Good morning, everyone. Before we start, I'd just like to mention this session is recorded, and if you have any questions, you can throw them in the Q&A. Andrew will have a Q&A session towards the end to answer the questions. Thanks again for everyone to join this month's TechTake talk. I'm Fred from the NCI training team. Before we start, the National Computational Infrastructure acknowledges, celebrates, and pays our respects to the Ngunnawal and the Ngambri people of the Canberra region and to all First Nations Australians, on whose traditional lands we meet and work and whose culture are among the oldest continuing cultures in human history. So today we are very grateful to have our very own NCI Associate Director, Andrew Howard, to give us some great insights about the NCI's newly commissioned cloud services, Nirin, and the Australian research environment R. Without further ado, I'll hand to you, Andrew.
Thanks, Fred, and thanks everyone for joining us today on an NCI Tech Talk. I'd like to start by acknowledging the traditional owners of this land on who we meet and pay our respects to elders past, present, and emerging. I'm Andrew Howard, Associate Director Cloud Services at the National Computational Infrastructure in Canberra, Australia. I'd like to give you an introduction to our Nirin Cloud and then move on to an introduction to Australian Research Environments, or ARE as we're calling it. Before I do, just a quick recap on what NCI is and what we do. We're a world-class high-end supercomputer and data services facility. We're a national tier 1 facility, one of 2 in Australia, and we enable high-performance computing, data storage and services, national data set hosting, curation and provisioning, and of course our Nirin Cloud. We directly support over 8,000 Australian researchers with approximately 44,500 unique users of our data services. We also host Gadi, which is Australia's fastest research supercomputer, clocking in at 9.28 petaflops. And when it debuted, it was the 24th fastest supercomputer in the world. And Gadi is over 7 times faster than its predecessor, Rygen. NCI is well connected to the rest of the world, and as part of the global research and education networks, we've got multiple paths leading from Canberra and leading from Australia, which connect us on the east coast of the US and New Zealand, on the west coast directly up to Singapore, and then across a number of different fiber services to reach massive data sets that we download from the US and Europe. So what makes NCI unique? One of the key differentiators of NCI is we bring together a range of capabilities and services. Our Guardi high-performance computing system, our Nirin Cloud, and our GData high-performance storage. They're combined into a single integrated research environment, which is really well connected. So we've got a number of 100 gig networks connecting all of these capabilities, and multiple 100 gig network feeds out of NCI up into ARNet. Our organization is divided across a number of service groups: high performance computing, cloud computing with data services, virtual research environments, data storage, visualization, and Hpc Optimization. So this is an introduction to Nirin, our cloud computing environment. We'll be looking at an introduction to what cloud computing is. I'll show you how to access it. I'll show you what you can do with it, and we'll look at how much it actually costs. So we commissioned some specific artwork for Nirin. The word Nirin comes from the Wiradjuri First Nations language and is the term for the edge. The Nirin artwork that you can see shows lines of communication, meeting and gathering places represented by the circular features. And then the art shape represents scientific communities researching in the Nirin Cloud, surrounded by their data. The Neuron Artwork was created by a Canberra Indigenous artist, Anthony Best, and was commissioned by NCI as part of our launch of the Nirin service. I should mention that the Nirin Cloud has been in operation for around 3 years. It took us some time to come up with the branding and ideation, but we're looking at a fairly well-established cloud. NCI has a proud tradition of offering cloud services, and this is about our 5th iteration of various cloud platforms. So we were challenged to repurpose our former supercomputer Rygen into NCI Cloud. Our cloud is OpenStack based. It occupies 22 racks. It's distributed across 2 data centers on the ANU campus. Contains approximately 1,400 Intel Broadwell cores, around 42,000 Intel Sandy Bridge cores, around 200 terabytes of memory. We've got 4 Intel Optane large memory nodes with 3.6 terabytes of memory each, 80 K80 GPUs, 6 petabytes of Ceph operational disk storage, which is available as volumes, CephFS or S3 based object storage. And we've got an additional 12.5 petabytes of Ceph object storage, which is currently being installed. This is all connected with a combination of 100 gig and 56 gig Ethernet interconnect. And the Sandy Bridge nodes form what we call a dispatchable zone, where we're able to power up and power down based on demand. So we regularly work across the Sandy Bridge nodes, trying to compact the load onto the smallest number of nodes possible based on the memory footprint. So this allows us to effectively utilize the power budget that we have, while also trying to remain as green as possible and not wasting energy where we don't need to. So let's look at what is cloud computing. In its simplest terms, cloud computing is a computing platform that you buy on a pay-as-you-go basis that somebody else does all of the maintenance and work on. It provides access to an on-demand computing, storage, and network capabilities, which are delivered over the internet. We'll look at the difference between on-premises versus public cloud, public, private, and hybrid clouds, and some of the deployment models: infrastructure as a service, platform as a service, and software as a service. The main differences between running equipment yourself, which is on-premise, and using a cloud service is typically related to the capital expenditure and scalability. In a university environment or a research environment, capital equipment funding can be quite complex to obtain. This also has an ongoing requirement for hardware and software maintenance on those systems, a requirement to perform ongoing security monitoring and maintenance, and of course the physical aspects of providing floor space, power, cooling, and managing a hardware lifecycle on the equipment. In the cloud, we've got dynamic scalability. We've already invested the capital expenditure, and we have enough capacity to allow our users to expand and scale up and down as they need. This provides you an on-demand, pay-as-you-go option for your computing requirements. Hardware and software on the cloud is maintained by NCI staff. This removes the requirement for you to worry about failing hardware. If we do start seeing errors in the underlying hardware, we're able to use a technique called live migration to move your current workflow to a better hardware platform, which gives us the opportunity to perform hardware maintenance on the underlying infrastructure, and also to perform ongoing upgrades and security fixes in a way that's completely transparent to the users of the cloud. The security aspect, we regularly scan for security vulnerabilities across all aspects of NCI infrastructure. We also perform network flow monitoring, looking for abnormal network flows, and we're investigating a number of trusted execution technologies, which will be used for application hardening. So to request access to Nirin resources, Nirin is available to the majority of NCI schemes. At the moment, if you could please contact your scheme manager to initiate the request for Nirin services. We have a number of different allocation schemes. So we're also building resource requests and management into the my.nci.org.au portal, which will allow you to self-service manage how your SU allocation to your project is spread across NCI, HPC, storage, and Nirin Cloud. And of course, Nirin resources are charged in standard NCI SU units, and the charge varies depending on the hardware environment that you select, either Broadwell or Sandy Bridge. I'd like to talk about some of the different types of clouds. Many of you will have heard of the main public clouds out there, Amazon, AWS, Azure, and Google Cloud. There are a number of other public cloud platforms which don't reach the scale of the three big platforms. Private clouds use the same sort of underlying technology to provide a virtualization and hardware infrastructure management capability. Private clouds are typically operated exclusively by a single organization and may use hardware that's on-premise or hardware that's located in a remote data center. And of course, hybrid clouds combine the flexibility of public clouds with the security of a private cloud. So one of the best ways to look at this is a public cloud is kind of like an ocean liner where everything's catered for you and you book a room or a cabin. A private cloud is where you have your own yacht, and a hybrid cloud is something like a ferry where it's shared by a number of people, but can also be used exclusively for your use. So as I mentioned, there's pretty much four sorts of cloud deployment models. On premises, which requires you to look after everything from the power and cooling, the networking, storage, servers, virtualization, operating systems, middleware, runtime, the data, and the applications. Looking at the next level across, which is an infrastructure as a service, which is what the Nirin Cloud offers to our stakeholders. We remove the need for managing virtualization, the servers, the storage, networking, power, and cooling. We provide a variety of operating systems running in our cloud, which are able to basically suit whatever requirements you have in terms of a Linux-based operating system application platform. In the infrastructure as a service model, we provide you a set of virtual resources that you can use to compose virtual machines or virtual servers that you use to deploy your applications on. In the platform as a service model, which we support by providing a number of scripts that are able to be used to configure the runtime, middleware, and operating system environment to deliver a platform. Typically, we will use templates to compose the underlying infrastructure and then use the underlying infrastructure to scale up or down. In a software as a service, typically you as a user use a managed software component. In the case of NCI, Australian Research Environments, or ARE, is a software as a service platform running over our infrastructure as a service Nirin Cloud. So infrastructure as a service is a composable pay-as-you-go compute environment. You're able to choose the number of CPUs, the amount of memory, the size of the volume disk storage, object storage if you'd like that as well, and public internet addresses. Our infrastructure as a service platform can scale up or down based on the requirements and is configured through our Nirin Cloud dashboard. I'll be giving you a live demonstration working through the dashboard on how to configure and stand up a virtual machine in the Nirin Cloud. In a platform as a service, you're using a pre-built application and runtime environment. We've curated a number of deployment templates for web services, data collection and visualization, analytics and development. Our help desk team can advise on the best way to activate a platform as a service offering using our infrastructure as a service underlay to provide the physical resources. And as software as a service or SaaS environment, these are ready to use research environments where the tools are curated and optimized by NCI. The environment and infrastructure are deeply integrated. And our teams have worked to optimize the application for the underlying hardware platform. Nirin is an infrastructure as a service cloud deployment, which provides you the framework for building dynamic, scalable, internet accessible compute systems. You choose the number of cores, amount of memory, size of the disk, number of external internet addresses, select a security or access policy, and your preferred operating system. We're also able to offer a high-speed connection to GData storage for projects that store data on GData and wish to use it in a cloud compute environment. The underlying system maintenance is completely transparent to users, where we use a technique called live migration to manage the underlying infrastructure. So we're able to move your instance around transparently across our data centers and between nodes in our data centers, which allows us to perform software and hardware maintenance and to reboot the physical servers if that is needed. And in our Nirin Cloud environment, we are able to use OpenStack snapshots, which allow the running environment to be saved and restored. This allows you to build a computational environment, potentially save it and shelve it, and then come back and use it at a later point without having to rebuild the whole environment. So there are a number of mechanisms of deploying on a cloud. The one I'm going to work through today with you is manually using the Nirin Cloud dashboard, but there are also a number of automation frameworks that can be used to actually create infrastructure as code. So you define all of the attributes of the compute environment that you wish to run, and then use one of the automation frameworks like Ansible, Terraform, or in a lesser sense, Puppet, to actually build the environment that will be exposed to the public internet or to your users via a specific security path. So let's switch to a live demonstration. Okay, so what you can see here is the Nirin Cloud dashboard. Once you've logged in, you're presented with an overview screen, which shows you the resources that you're currently consuming. Some of you will be connected into multiple projects, and each project has a unique set of quotas and limits. The drop-down menu at the top of the screen allows you to select which project you're currently working on. In this case, I'm working in one of our internal cloud projects, which is our migration project. This was used to move instances and data from our previous iteration of Cloud Tension over to our Nirin Cloud. So as you can see here, we're able to see the number of virtual machine instances that are running. We have a quota of 32 virtual CPUs, 164 gig of memory, of which we're using 44 gig. We're currently not using any, we've currently got 138 terabytes of volume storage allocated of the 200. We're using 3 of our 3 allocated floating IP addresses with a number of security groups, networks, ports, and routers. Typically, we'll assign you enough quota based on your requirements We typically give projects 2 floating IP addresses, but are able to allocate more if there's a particular use case. So what I'd like to do is spin up a small virtual environment and just show you how it works. So I'm just logging in. So we'll just go back to the overview screen that we saw earlier. Let me just walk you through. So what we've got is the capability to define virtual environments in terms of their compute, their data storage, the volumes, their network capabilities, and their object store capabilities. Let's spin up a small core compute environment. So we choose the launch instance. We'll enter a name for this instance and then click Next. We support a wide range of Linux-based operating systems on our Nirin cloud. What I'm going to do is search for Ubuntu Focal. And you'll see here that we've got a number of focal images. Typically, we will track our upstream operating system providers and bring in the current cloud image, which is available from those upstream providers. As you can see, the most recent update is at the bottom, which is our 220419 focal cloud image. So we'll add this image, which will become the basis of our operating environment. Then we click Next. We're now able to choose the hardware configuration that the virtual environment will be built with. We use a terminology called flavors, which are basically predefined virtual machine environments that we've created, which meet the majority of needs that our users have. We're also able to create what's called private flavors, which are able to use a lot more resources. And we'll typically configure those if you have a requirement for large memory or GPU nodes. So I'm just going to select a fairly small flavor here, which is 4 gigs of memory, a 10 gig root disk, and no ephemeral disk. Ephemeral disk is a temporary storage area that, as its name says, is ephemeral and is lost when you shut down the virtual machine. We're also able to attach external volumes. So if you wish to preserve data across multiple virtual machine reboots, the data must be copied into the root disk on the virtual machine or onto an external volume. Any data stored on the ephemeral can be lost and can also be lost during live migration. So we've just moved on to the network section. By default, each project has an internal network. In this case, I've renamed that internal network as migration. An internal network is basically a private address space network. For those of you familiar with TCP/IP, our network, you will be allocated a network in the network 10, which is a private network address range. You can specify security groups, and a public floating IP address can be assigned to this, which will allow access from the outside. The reason that we have a private internal network is typically so you can have an externally facing web or proxy server, which is talking to an internally facing set of worker nodes or worker instances, which allow the scale out and scale up and down of workloads as needed. So I've selected the default network that we're using. Now, quite critical on this is a concept called security groups. By default, instances in the Nirin cloud do not have external internet access. It's necessary to create a security group and then to add that security group to an instance. Security groups can be edited and managed while an instance is live. But in this case, we've got a security group which enables SSH access, which happens on what's called TCP port 22. There are a number of well-known ports for services. If you're on a Linux system, you can identify what port is connected to which service by looking in the /etc/services file. That will give you the port number to service name mapping. In this case, we're going to add SSH access, which will allow us to SSH into this instance to perform post-initialization configuration. As part of building a virtual environment, we use the concept of public and private keys. So public and private keys are an encryption technique where you generate a key. One part of that key is public and can be distributed out to other people. The other part of that key is private. So when the public key is presented to a service which knows the private key, you're able to log in without a password using what's called cipher chain technology and present your public key using your SSH client. As you can see, I've got a number of public keys configured. Let's select my personal public key, which will then allow me to SSH into this instance after I've created it. Now, there are a number of ways that you can actually configure your environment within OpenStack. The simplest way to bootstrap an environment is to use the customization script, which is present on the configuration tab. This will allow you to run a series of commands that are executed as the virtual machine is started up, and can be used to do things like perform software updates, install specific environments, pull a repository out of Git for use for deployment, or pull down a set of configuration scripts which are also used for deployment. In this case, all I'm going to do is do an update and then an upgrade to make sure that I've got the current version of all software installed. Server groups basically allow you to group servers in a number of different domains. This is really useful for managing, as I mentioned before, a scalable environment running on the inside of a cloud in a private network, with the external presentation addresses presenting out to the public internet. In this case, we don't need to specify anything in this screen. Scheduler hints also allow us to specify particular requirements in terms of underlying hardware architecture. For most Nirin users, this screen will not be used, but we do use it in some cases for tagging particular GPU instances. So you may need to use it in that circumstance. It's very rarely used though. We also have a range of metadata, resource metadata, which provides a template for things like database software, runtime environments, and web servers. In this case, we're also not going to be using that. We're just going to be building an instance by itself. So I've now clicked Launched Instance. You'll see that it's spawning. This will take a minute or two to start the instance up, attach and create the virtual disk, and we'll then attach a public IP address so that the instance is visible to the outside world. So our instance is now running. Let's take a look at what happened during startup. So if you look at the instance itself, we'll just go back to the instance screen. We can perform a number of actions on an instance. We can associate public IP addresses. We can attach or detach network interfaces. We can attach or detach volumes. We can edit the security groups. We can access the console. We can view the log. We can rescue an instance, which rebuilds the instance from the template that you used to create it. You can pause an instance. You can suspend an instance. Shelving an instance, basically, so Something I should mention is paused and suspended instances are still charged. So if you wish to keep a copy of your resources or your configuration and virtual machines, we do request that you shelve the instances. This moves them onto a storage service rather than allocating memory. In some cases, the cloud team may lock an instance. This occurs if we detect a security issue or a vulnerability or a compromise of a virtual machine. And typically our user services team will reach out to you and advise you if we've detected a vulnerability and suggest methods of remediation. You can also soft reboot an instance, which is equivalent to hitting Control-Alt-Delete on a physical server. Hard reboot an instance, which is like turning the power off and back on again. Shut off, which is like powering down a virtual machine. Rebuild or delete an instance completely. So let's look at the console just to check that our instance started up correctly. So you can see there that we have a console. We can use that to actually log into the machine and manage it. Currently, we have not set a user accessible root password, so it would be necessary to access the machine via an SSH interface. Let's look at what happened during startup. As you can see, our public key pair, or the private side of our public key pair, was injected into this instance. And our Cloud Init script ran, which performed a software update on the machine. What I will do is go and associate a public IP address. As I mentioned, when instances are created by default, they only receive what's called a private IP address, or an address in the network 10 range. Each tenancy has its own private address range. So to reach this from the outside world, it's necessary to add what's called a floating IP address, which connects the inside network on this instance to a publicly addressable network, which can be used on the internet. We'll now see here that the machine has two IP addresses, one which is the internal network address, which is in network 10.0.0.240, and then a publicly available address, 130.56.246.227. I can use that publicly available address as the mechanism I use to actually connect into the instance, and then perform additional software configuration to build a runtime compute environment, doing things like installing a web server, installing a database, or installing a range of other software. So what I'm going to do is stop screen sharing now and go back to my keynote presentation. Now I've walked you through how you use the dashboard to stand up your first virtual machine instance on the Nirin cloud. So we've walked through the overview. We've looked at creating a new instance. We've chosen an operating system, which was one of the supported Linux distributions, CentOS, Ubuntu, Rocky. You can also upload your own operating system image if you wish to. We've used the Nirin dashboard to choose an operating system. We've chosen a flavor, which defines the number of CPU cores, the RAM, and the operating system root disk storage. We've chosen the network, which was our internal network. If you've requested access to GData, you'll also see we'll also build a what's called a private network, which connects your tenancy to one of our GData NFS servers, and then we'll provide you with additional information in how you mount that GData resource into your cloud instance. We then selected which security groups we wish to use. The security groups control which network ports can be accessed from the internet. Some examples of this are SSH, which runs on port 22, and the traditional web protocols, HTTP, which runs on port 80, and HTTPS, which runs on port 443. We then allocated a public IP address, which allows our virtual machine or instance to be accessed from the outside world. We selected the security groups, and then we're able to SSH into that instance using an SSH client. So that brings us to an end of a very brief introduction to cloud computing. I'd like to move on to discuss one of our software as a service offerings, which is Australian research environments. Before I do, I really should position where Nirin fits compared to ARE. At NCI, we've got a very diverse range of users, ranging from those who are deeply technical, who understand all of the aspects of the compute environment they wish to build, all the way up to users who really just want to use the utility of NCI and don't want to worry about installing local software. We really have tried to reduce the barrier to entry of high-performance computing by introducing our Australian research environments. So let me give you an introduction to ARE, or Australian Research Environments. We'll look at what it does. We'll look at how you access it, what you can do with it, how you can request additional applications, and how much it costs. So ARE is a web-based graphical interface to both our NCI Guardi Hpc environment and our Nirin cloud. It's based on the Open On Demand application developed by Ohio Supercomputing Center. And one of the key benefits is that there's no need for local software installation for an SSH client, an X server, an FTP client, or any other tools. You're able to directly access NCI's core facilities and core capabilities directly from a web browser anywhere on the internet. So to access ARE, just go to are.nci.org.au. And log in with your NCI username and password. As you can see here, here's the landing screen for ARE. We've had virtual desktop environments in a number of forms for around a decade. Typically, these have used a technology called Strudel, which connects an internally facing virtual desktop environment to an application or client running on your local workstation, which allows you to remote that virtual environment. With ARE, we've incorporated this completely into a web-based interface, and you no longer need to install any special software. I should mention that we have had a number of trials and different test versions of our Open On Demand environments leading up to ARE. If you're currently a user of one of our Open On Demand environments, we'd strongly encourage you to switch over to ARE, as this is receiving the majority of the support and new applications are being rolled in every couple of weeks. So what can you do with ARE? What we've done is added some of the most common graphical applications to ARE, and added the existing portfolio of Gadi applications through the familiar module system. Our teams are working on adding additional applications. We always like to know what you need. I'll show you a couple of example applications that we've already incorporated, but we're working on more, and we expect to release another update to the ARE application set around the end of next week. ARE also provides a Guardi Terminal that can connect you to a Guardi login node, and we're able to give you access to graphical, both regular CPU and GPU enabled environments for Jupyter Lab, Studio, and virtual desktops, which are used for Linux-based visualization environments. So this is the home screen of ARE. As you can see, this is our initial release, where we've got 4 applications currently built in. Jupyter Labs, which is an interactive visualization, development, and data analysis environment. Our virtual desktops, which is incorporating a large number of the tools and facilities that have been available in our discipline-specific virtual desktop environments. Our teams are still doing some more work in terms of customizing discipline-specific versions, but we'll be adding the majority of tools into the general virtual desktop environment while we work on more specific discipline-specific environments. We've also got a GPU-based virtual desktop environment and a Guardi Terminal, which allows you to connect into Gadi without needing to install a local SSH client. If you'd like additional applications installed into ARE, please contact the NCI help desk, help@nci.org.au, and one of our friendly help desk team will pass that request on to our applications development team, and will add your application into the roadmap for applications to be added into ARE. Once you click on an application, you're provided with a range of options. ARE sits on top of the traditional Guardi queuing system. So you have a range of options in terms of which Guardi queue that you'd like to use. Typically, we have defaulted ARE access to using a normal Broadwell queue. And you'll be charged the standard SU rates based on the queue you select. So what you're able to do is scale out to use all of the capabilities of Gadi, including the Express IO nodes, GPU nodes. You're able to specify the number of CPUs that you would like to occupy, which will allocate a proportionate amount of memory. But just be aware that the queue you select will determine the application charging cost ratio to run under ARE. What we've tried to do, though, is make this as affordable as possible. So experimenting with ARE using the default options should be very low cost in terms of SU utilization. So we've basically worked through that initial screen in ARE, and we'll be providing a more detailed set of tech talks with one of the ARE developers, detailing exactly what all the options and the interaction between those options are. But as you can see here, we've requested a Jupyter Lab session, which has been queued. This may take a minute or two, just depending on the load on Gadi. And as I mentioned, it uses Gadi's normal queuing systems. So after a minute or two, we're then presented with an additional button, and the status has changed from queued to running. And that will allow us to open an interactive Jupyter Lab session. So if we click on that button, we're presented with a Jupyter Lab. We're then able to type Python commands into that Jupyter Lab. And once we've finished, as I mentioned, you're able to specify the number of wall time hours or the amount of runtime that this particular job will have before it is terminated. Please just check if you do leave the job running, it will consume the entire amount of the wall time that you've specified. So it's important that you, if you're finished using one of these resources and don't want to be charged for it, that you delete the resource afterwards. So we've finished with our Jupyter Lab session. We've selected delete and confirmed. That's destroyed our Jupyter Lab session and returned us to the ARE desktop. This is the same operation, launching a virtual desktop environment. As you can see, it's the familiar Mate desktop, and the applications are available on the menus at the top of the desktop. Something I should mention is that the file manager within the desktop has access to all of the GData volumes that you have specified, and can be used to perform file management operations on your GData and home directory and Scratch directory. So I started up the ParaView application, which is a graphical environment used for analysis and visualization. And just closing off on the application mix, this is a Guardi Terminal, which is basically an interactive SSH session, which will reproduce your normal login to Gadi. So ARE costs is based on Guardi SU allocations, which are dependent on which queue you use. So selecting normal BW or Broadwell is the lowest cost option, with all other queues increasing cost over there. And the SU charge rate depends on the size of the resource, the number of GPUs, CPU cores, memory, and of course the queue selected, as I just mentioned. So with that, I would like to finish off my presentation and thank you all for attending today. If you have any questions, please feel free to reach out, and if I can answer anything that I haven't covered, more than happy to do so. So once again, thank you very much for your time.
Thank you, Andrew, for this very useful, informative talk. I got a couple of questions to throw in. So I guess first question is, how affordable is using Nirin? Since I was just picturing some usage cases in my mind. I guess one typical usage would be, for me, I would like to host my research, self-hosting research related pages, say MediaWiki. Is there something suitable to do so on Nirin? Because this is self-hosting, so I suppose users would like to have them to running 24/7 for a long period of time. So that would bring the high cost, or?
No, we've typically tried to price Nirin significantly lower than our commercial cloud competitors.
Right.
The use case that you presented of a long-running web service for research data or a portal is one of the exact use cases that Nirin is designed for. So I'd rather not go really specific on the pricing, but we've made it very attractive, and we've got a range of CPU options that are available, anything from a small one-core virtual machine all the way up to multi-core with large memory. We can provide you a range of options at range of price structures, but we believe we've come in with a very attractive offering for existing NCI users.
That's good to know. I have a second question, but I'll leave the other users to ask questions so I don't block the queue.
Hello, I can see a question from you. Would you like to
yes,
unmute
can you hear
and
me?
ask a question?
So the former cluster Rajin has quite powerful CPUs. So one question is, even if you request one CPU, it might be like too powerful, let's say, for small applications. If you are just browsing in the cloud, you are doing a small scale task. So I just wonder, when you select one CPU in the virtual machine, is that one core of the actual machine, or is it like virtualized somehow so that it doesn't use that much resources?
So just depending on which flavor you select, some of the flavors are directly attached one-to-one on a CPU. Others share their CPU. So the default flavors that we provide are running on a shared CPU complex. What we do is use Live Migrate to balance the load over the available CPUs to ensure that you see almost real-time performance of your CPU. We've currently got 3 generations of CPU, or about 4 or 5 actual, but we're presenting 3 generations of CPU within the cloud. Sandy Bridge generation, which is the majority of the old Ryzen nodes. Broadwell configuration, which reflects the underlying nodes used to support ARE, and also Optane, which represents Skylake architecture for a large memory node system. So yeah, we give you the choice of providing a CPU that is the right size or scale, and you're also able to change the underlying CPUs by rebuilding an instance.
So I guess do you have like recommended configurations? Let's say I'm running like a dashboard, a data science dashboard, or something that is actually not just presenting data from a database already calculated. So or versus I need to do some machine learning tasks that requires more, is like different configurations for each of the machines, or?
So in the machine learning case, we would typically allocate dedicated hardware resources running on one of the K80 nodes. There's basically no kind of hard and fast rule I can give you in terms of how big the scale should be. My recommendation would be to choose our default Broadwell flavors. Something that I didn't mention is that we're spread across 2 data centers. Our primary data center has continuous power availability. Our secondary data center may suffer a 3 to 5 minute loss of power around once a year. So we've called that the scalable zone. So typically a long-running web service would run on the Broadwell nodes in our availability zone rather than the scalability zone. But we're happy to work through that on a case-by-case basis if you need more guidance on that.
Okay, thank you.
Cast and another one. So a while ago I heard I remember someone commenting on the sort of comparison between traditional cluster and the cloud computation. And the example I heard at the time was comparing I guess a decade ago, Blue Gene P and Q, those sort of Rolls-Royce of HPC, and they are tuned so well such that when you submit 2 identical jobs at separate times, and the runtime, the wall time will be predicted basically identical, just in a milliseconds. That's what the people, that sort of quality of service they got. I guess with the advantages, all the advantages of cloud computation, they also say the running time, if you do the same sort of procedures cloud, you have somehow or somewhat you will get quite variable in the running time. Do you think it's still true, sort of in the context of Nirin or R?
So that question is kind of a little difficult to answer. The execution time of a particular task is really going to depend on which generation of CPU architecture that you're running on. Nirin, as I mentioned, repurposes the previous generation supercomputer, and as such doesn't have the absolute latest generation CPUs currently available. They're only available in our Gadi compute environment. However, we do have a massively scalable compute environment where your applications are needing something like MPI or are highly embarrassingly parallel. We're able to scale out to an unprecedented range of compute nodes, and provided the workload can be distributed amongst compute nodes, we can scale out to meet your compute demands. However, NCI being an integrated facility, we typically would suggest the most appropriate platform for the most appropriate job. And in many cases, our Guardi HPC environment is more suited to some of that deeper and more IO-intensive data analysis or data processing work. That's purely a function of the way that the Guardi system is interconnected, which uses a technology called InfiniBand, which is far more efficient than the TCP/IP networking technology that we run on the internet. So our Hpc Optimization team are really well equipped to guide you in terms of the best way to implement your code to work in the most performant way across a variety of our platforms. So we'll typically try to give you the best option, which will meet your computing requirements on the most appropriate platform, so that you can get your research done in the fastest amount of time and with the less amount of hassle.
Thanks, Andrew. Yeah, I guess we have really depends on users' jobs and their execution tasks.
Yeah.
With that, I'd like to thank Andrew again for giving us this wonderful talk. I guess we'll quit today.
Thanks, everyone. And we're always keen to hear your feedback or suggestions. So please reach out to help@nci.org.au if you'd like to speak to any of us directly, or if you'd like further information or guidance on how to configure an environment.
Thank you, Andrew. Thanks for your time.
Thanks very much, everyone.